You know, we all want the dream EV, right? One that charges up in minutes, launches off the line like a supercar, and can go for hundreds and hundreds of miles. But there's this one huge invincible wall standing in the way of that future, and that wall is heat. So today, we're going to dive into that hidden battle every EV engineer is fighting, and the amazing breakthrough that might just solve it for good. Yeah, it really all boils down to this one simple but kind of brutal equation. As engineers try to cram more and more power into smaller and smaller electric motors, those motors generate an insane amount of heat. And right now, heat is the number one enemy of performance. Okay, so why is this such a huge deal? Well, let's be honest. The demand for high-performance EVs is just off the charts. We're all craving that instant acceleration that pins you to your seat, and we want a driving range that makes us completely forget that gas stations were ever a thing. Now, to meet those demands, automakers are developing these incredible new motors that really seem to check all the boxes. They've got way more power, packed into a smaller package, they're super efficient, and that all translates directly into more miles on a single charge. But as you might guess, this leap forward comes with a hidden price. And that price is heat. A ton of it. Pushing that much power through such a compact motor is like giving it a constant raging fever. If you can't pull that heat out fast enough, the motor overheats, its performance gets slammed down, and in a worst-case scenario, key parts can start to fail. So what in the world is making these new motors run so hot? Well, a huge piece of the puzzle is this really brilliant piece of engineering called a hairpin winding. So instead of using the old school round copper wires, which actually leave a lot of empty space, this technique uses these flat rectangular copper bars that are bent into a hairpin shape. And the difference it makes, well, it's way easier to show you. Think of it like this. Using traditional round wires is like trying to pack a jar full of spaghetti. You're always going to have a lot of air gaps and wasted space. But hairpin windings, that's like neatly stacking perfectly fit copper bricks. You get way more copper into the exact same space, which means less electrical resistance, way higher efficiency, and a huge boost in power. But here's the catch. Now you've created this incredibly dense, powerful heat source that's packed into a super tight space. The old ways of cooling a motor, they just can't handle it. The big question becomes, how on earth do you get coolant deep inside that bundle of copper bricks to pull the heat out from the very core of the motor? And you can't just, build a motor and cross your fingers hoping the cooling works. You have to simulate it first on a computer. The problem is the traditional methods for this, like computational fluid dynamics, or CFD, are painfully, unbelievably slow. We're talking days, sometimes even weeks, for just one single simulation to run. And this comparison just says it all. The old way, a full CFD analysis, could take more than 120 hours. That's 5 full days, just to test one idea. You can't really innovate at that speed. But this new method we're talking about, it gets the answer in less than 30 seconds. That's not an improvement, it's a revolution. So here it is. This is the breakthrough. It's called a high-fidelity lumped parameter thermal model, or LPTM. But think of it as a digital twin of the motor. Instead of simulating every single tiny molecule of oil, it smartly simplifies the motor into key zones and predicts how they'll behave. It's like having a super accurate digital crystal ball that can tell you the temperature of any part of the motor almost instantly. So how does this whole thing work? Well, first, the engineers feed the model the exact physical design of the motor. Then, the system builds a sort of thermal map, breaking the motor down into all these interconnected points. Now, here's the magic part. It then calculates all the complex physics of how cooling oil gets sprayed onto those hot copper windings. And finally, it checks its own work against real-world data to make sure that its digital twin is a perfect match for reality. The real power of this model is its incredible attention to detail. It's basically simulating the motor's entire cooling circulatory system. It figures out how the oil spray hits the windings, how it sneaks through tiny internal channels, and it even accounts for tricky stuff, like how some surfaces might not get perfectly coated in oil. It even tracks how the oil itself gets hotter as it does its job. But look, a fancy computer model is pretty useless if its predictions are wrong, right? So the researchers behind this had to put their digital twin to the ultimate test, a real-world showdown. They built a physical prototype of the motor, covered it in temperature sensors, and ran it hard. And the results were just stunning. The biggest difference between what the model predicted the temperature would be and what the sensors actually measured on the real running motor was less than 3.3 degrees Celsius. That is an absolutely incredible level of accuracy. It proved the digital twin wasn't just making a good guess, it was a true mirror of reality.
And you don't have to take my word for it. The researchers themselves summed it up in their paper. They said the results agree well with the real-world experiment. Now, in the world of science, agree well is a massive understatement. It's their way of saying, yeah, this thing works. It's not just fast, it's incredibly reliable.
So let's bring this all back home. Why does a fast, accurate computer model actually matter to you and me, the people who might drive these cars one day? Well, because it completely changes the game for how quickly EV technology can evolve. I mean, just look at this chart. The visual says it all. What used to take 5 days of a supercomputer chugging away can now be done in about 10 seconds on a normal computer. This isn't just a small step forward. It's a monumental leap that unlocks a pace of design and development that was literally impossible before.
Think about what this really means. With a tool this fast, an engineer can try out thousands, not dozens, thousands of different cooling designs in a single afternoon. They can tweak nozzle placements, change oil flow rates, and find the absolute best, most efficient way to cool a motor before a single piece of metal is ever cut. And that leads directly to more powerful, more reliable, and just plain better electric cars for all of us.
And that kind of leaves us with this final, really exciting question. If engineers have just been handed a tool that lets them solve one of the biggest problems in EV design in seconds instead of days, what happens next? What performance barriers that seem out of reach today are suddenly going to get smashed tomorrow? This research might just be the key that unlocks that future. Thanks for tuning in.